Okay, so to put all this together and keep in mind the two major kinds of bonding, ionic over here, covalent over here, and sort of summarize what we've done so far. The first type of naming system we learned, the nomenclature, how to name a compound, how to figure out the formula, and how to figure out what it looks like when it comes together, was binary ionic. So that's when you have a metal and you have a nonmetal. There's only two different elements involved, right? So it could be like magnesium and oxygen, and they give electrons and take electrons, forming a compound. The second thing we talked about were the polyatomic ions. So we have 11 of those that you need to keep in mind, memorize their formulas and their charges, the names of those, and all those are basically our groups of nonmetals that need an extra electron or two or give away an extra electron to become stable, and they are going to bond with metals, so because of that they are under the ionic column. The third one is where we started using the stock system. So we have to use this appropriately. Like, when do we need this? We need this when we have a transition element other than zinc and silver. We also want to use it with tin and lead, and we want to make sure that we only use it with those elements that require it, that have a variable charge. We then got over here into the covalent side and talked about the binary covalent compounds, which are those that have just two different nonmetals involved. Could be a nonmetal with a metalloid, because metalloids, remember, they act like nonmetals, so either taking electrons from a metal, which is ionic, or sharing with another nonmetal if that's covalent. Also over here we have the strong acids. So there are 7 of those that fall into that category. Remember that the strong bases really are going to be over here, because they are just the group 1 elements and the bottom end of the group 2 elements with hydroxide. So that's really just already covered by polyatomic. And the sixth that we just looked at were the hydrates. So here you have ionic compound, and there's some water attached. The water is attracted to the charges, and it attaches after orienting the positive side and the negative side, partially positive side and the partially negative side, oriented to those ions. So then there would be a seventh one, which is like a whole nother study, a whole nother subject of study, like entire semesters of college chemistry where you deal with organic compounds. And we just rough, roughly, touched a little bit about the kinds of groupings that were the alkanes, the alkenes, the alkynes, and benzene. And so that's what we looked at. And just to kind of keep in mind the characteristics of each of these things, the ionic compounds are going to be where you have a metal with a nonmetal. So the first thing you want to look for is, do you have a metal? Because if you have a metal, you're automatically going to be over here in the ionic compound grouping, and it's going to be with a nonmetal. For covalent compounds, they're non-metals only. So if you see a metal, you're going to be over here on the left-hand side with the ionic compounds. Ionic compounds give and take electrons, whereas covalent, they share electrons. For ionic compounds, we use the crisscross method. To figure out what the formula is, we have to crisscross the charges. For covalent compounds, there are no charges, so we use prefixes to indicate how many of each atom there are. In ionic bonding, when we're forming the compound, we form ions, the cation and the anion, and they attract together. And over here we form molecules. So molecules are formed, which are a group of nonmetals that are covalently bonded. And lastly, one item to keep in mind is that ionic compounds will produce one formula. So for every situation where you have a certain ion and a certain other ion, they'll crisscross and they'll make a single formula. Whereas for covalent compounds, we can have many formulas. We talked about the idea of carbon being able to bond singly, doubly, or triply, and the fact that it can bond to as many as 4 other atoms. So you can make long chains of carbon atoms, and you can have many, many formulas, even with just 2 elements. Let's just C and H. You can have many, many different formulas with those 2 elements. Whereas on ionic bonding, you end up with, for like magnesium with oxygen, exactly one formula, only one way in which that works. So then to review what it actually looks like, an ionic bonding situation, if we had beryllium fluoride. So we have beryllium and fluorine, so it would be beryllium fluoride. And if we figured out the formula for this, we know that Be, being an alkaline earth element, is -2, and fluorine, the halogen, is -1, so +2 and -1, so 1 to 2. And so the formula would be BeF2. And then what does this look like when you try to show the compound? Here's Be, it has 2 outermost electrons. Here's F, which has 7. Beryllium can give away 1 to fluorine, which becomes -1, and that fluorine now has the octet. And another fluorine is required for beryllium to give away 1, 2, and it becomes -1, and that has the octet. And beryllium now has lost the 2 outermost electrons that were in its highest energy level. So now it has the octet because the level below is full. So that's what you want to show. Like if you're going to, I just did a flip book basically right there. Just showed you like, okay, here's one atom, beryllium. Here's another atom, fluorine. Here's the electron being transferred. Here's another fluorine. There's the electron being transferred. And here's the charges. And there you go. This would be like the last page of the flip book to show that. You have to show what atoms are involved, how they become ions, what the formula is, what the name is. There's a flip book for an ionic compound. Over here, if I had dicarbon hexahydride, then, well, sorry about that, can show how those come together. Dicarbon hexahydride is 2 carbons and 6 hydrogens. And so how would that bond together? Well, each carbon has 4 valence electrons, and each of the hydrogens has 1, and is looking to have 2 to become like helium. So each of the hydrogens comes along with its 1, and they share. So each of the hydrogens becomes more like helium, which has its version of the octet, which is just 2. And then I can show that this carbon on the right has 2, 4, 6, 8. And this carbon on the right has 2, 4, 6, 8. And so then I just did another flip book. This flip book would be for dicarbon hexahydride. I introduce carbon and hydrogen and show how they bond. This is covalently, though. Notice there are no positive or negative charges anywhere, and this compound is the formula is C2H6. Now, if we talked about the organic name for this, then this would be called ethane. So we can talk about the organic name of it also, if we want to introduce that, which is the fact that it has the 2 carbons, and the 2 carbons are singly bonded together.